Every year, over 500,000 bridges are built worldwide, but only a few of them challenge nature and time. To create a giant capable of withstanding thousands of tons of steel, windstorms, and earthquakes, engineers first dive into the very heart of the Earth, drilling the ground to a depth of over 100 meters, studying every layer of rock. Here, under water and mud, the foundation is born, on which the fate of the entire structure depends. How do machines weighing as much as houses place piles with millimeter precision? And what will happen if even one of them shifts? Watch until the end, and you will learn what the engineering elite keeps silent about. The construction of long bridges begins long before the first steel beams or concrete supports appear. It all starts with a site investigation. Engineers analyze the soil, the strength of the current, the level of seismic activity, and the depth of the bottom, if it's a river or a bay. Often, special drilling rigs are used to take rock samples at depths of over 300 feet. These data determine the type of the future bridge: suspension, cable-stayed, or beam. After this, a three-dimensional model is created. It takes everything into account: the load from transport, the force of the wind, temperature fluctuations, and even the possible impact of waves during storms. For bridges longer than half a mile, the permissible error in calculations can be no more than a few millimeters. Otherwise, the structure may lose stability. When the construction of a bridge moves from drawings to the actual ground, one of the most responsible and complex stages begins: the construction of the foundation, or the pile foundation. It is these structures, hidden under water or earth, that support the weight of the entire bridge: thousands of tons of steel, concrete, transport, and even wind load. Drilling cranes arrive at the site, giant machines with a long mast, a hydraulic drive, and interchangeable drills. They can reach the height of a 3-story building. Steel piles are brought to the worksite. Usually these are pipes with a diameter from 3 to 6 feet and a length of up to 100 feet. In marshy or marine areas, the piles are even larger, sometimes up to 150 feet. The drilling process takes place in stages. The machine is positioned with an accuracy of a few inches. For this, laser and GPS systems are used. Then the operator lowers the drill into the ground. The powerful rotation of the bit crushes the rock, and a hydraulic system pumps out the resulting pulp. In some areas where the soil is unstable, drilling is carried out with the immersion of casing pipes, metal casings that prevent the walls of the well from collapsing. When the hole reaches the specified depth, a steel pipe, the pile casing, is installed in it. A reinforcing cage is lowered inside, which strengthens the structure, after which concreting under pressure begins. Through a special hose, a concrete mixture is supplied from the bottom up, displacing water or mud. Thus, a dense, air-free mass is formed, which over time hardens into a monolith. In marine areas, floating barges with drilling rigs are used. Divers control the position of the pile underwater, and engineers monitor the process with ultrasonic sensors. In a strong current, drilling is carried out only during periods of calm, when the wave level is minimal. When the piles are installed, their tops are cut to the required height, and capitals are mounted on them. Large concrete blocks that unite several piles into one support. After this, pylons or columns are erected on these foundations, which are already visible above the surface. On land, temporary sites are simultaneously set up. These are logistics centers where beams, cables, reinforcement, and concrete sections are stored. Often, huge cranes 300 feet high are used here, which can lift blocks weighing over 200 tons. When the supports are ready, the turn of the superstructure comes. For bridges of great length, 2 main technologies are used: suspension and cable-stayed. In a suspension bridge, the main load is carried by steel cables. To secure them, 2 massive towers, pylons, are first erected. Their height can reach 700 feet, as in the Golden Gate Bridge in San Francisco. The towers are assembled in sections, lifting each one with a crane and connecting them with bolts and welding. After the installation of the pylons, the main cables are stretched between them. This is a complex process that is carried out in stages. Thin steel wires, the thickness of a finger, are stretched one by one, by the hundreds, until a main cable several feet thick is formed. Then vertical hangers are attached to these cables. They will hold the roadbed. In cable-stayed bridges, the main load is transmitted through inclined cables that go directly from the towers to the sections of the roadway. Such cables are made of steel strands with a polymer coating, capable of withstanding a load of over 500 tons. They are installed with the help of hydraulic winches, which precisely regulate the tension. The installation of the span sections is one of the most impressive stages in the construction of a bridge, when the giant engineering structure literally begins to connect the shores. Each section is a finished fragment of the road, made of high-strength concrete or steel at a specialized plant. There they are formed in giant molds, reinforced with steel bars, treated in thermal chambers for rapid strength gain, and then marked and checked for accuracy with a laser system. After this, these blocks are transported to the construction site. If the bridge is laid across a body of water, the sections are delivered by barges, floating platforms capable of withstanding hundreds of tons. On land, they are transported by multi-axle trailers with dozens of wheels, which evenly distribute the weight. The movement of such columns is usually accompanied by police, as each block can be from 100 to 400 tons and over 100 feet long. At the construction site, floating cranes or lifters are already waiting. These are powerful lifting systems capable of lifting a load of over 500 tons. Most often, such cranes are mounted on pontoons or mobile platforms that can accurately maneuver over the water. During the lift, the crane operator coordinates his actions with the engineers who are on the bridge supports. Every movement is a matter of inch precision, as the section needs not just to be lifted, but placed perfectly in the design position. When the block is suspended above the supports, it is slowly lowered. Workers fix the position with the help of special guide pins and laser marks. Then dampers and high-strength connecting bolts are installed in the joints of the sections. It is important that the sections fit together without the slightest misalignment. Even an error of half an inch can cause uneven load. Next, the joints are filled with cement mortar under pressure, which fills all the voids and forms a monolithic connection. In some types of bridges, post-tensioning cables are used, steel strands that are threaded through the internal channels of the sections and tensioned with hydraulic jacks, providing additional strength. If the bridge is being built over the sea, the installation is even more complicated. Barges with sections are tied to positions with an accuracy of a few feet using GPS, and the lifting takes place only in calm seas. Often at night, when the wind is weaker and the waves are minimal, the crane slowly lifts a section. The process can take several hours. From the side, it looks like a giant aerial operation. A steel or concrete slab, as huge as a two-story building, smoothly rises above the water or a gorge, moving with an accuracy of a few centimeters. When it is fixed between the supports, the bridge literally grows. Another span, another few tens of feet of road, which bring it closer to completion. In parallel with the installation of the roadbed, communications are laid, lighting systems, communication wires, pipes for rainwater drainage. Most bridges have sensors that measure vibrations, temperature, the tension of the cables, and even the concentration of salts in the air. These data are constantly transmitted to a control center. When the main structure is completed, the road surface work begins. The surface consists of several layers. The first layer is a special anti-corrosion compound that protects the concrete and metal. Next, waterproofing is applied, then several layers of asphalt or polymer concrete, about 4 inches thick. For suspension bridges, lighter materials are used to reduce the load. The final stage is the installation of railings, noise barriers, and the painting of steel elements. The painting has not only an aesthetic function, it also protects the metal from corrosion. For bridges over the sea, paints with the addition of zinc are used, which create a stable protective layer. After the completion of all work, the bridge undergoes a series of tests. Special trucks are loaded onto it to check how the structure reacts to weight. Vibration tests are also conducted. Engineers check how the bridge behaves during wind or the movement of trains and cars. If the indicators meet the standards, the object is put into operation. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. Only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks, connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured. And two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. And the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. and the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained three substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture. And chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these three products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds: pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies. Today, we're embarking on a journey to one of the coolest and smartest factories in the world of woodworking. We're going to talk about how people looked at ordinary wooden floors, which fear moisture like a vampire fears garlic, and said, "Dude, we can do better." Thus, engineered hardwood was born. This isn't just a board, it's a true wooden club sandwich, a brilliant work of engineering where the beauty of natural wood is combined with superhuman stability. This is the story of how a floor that laughs in the face of humidity fluctuations is born from several different trees, a giant glue juicer, and an infernal ultraviolet tanning session. It all begins not with one, but with two different forests. The first forest is a runway for supermodels. Here grow those noble trees whose beauty makes the heart beat faster. Majestic oak, strong hickory, elegant maple, or luxurious American walnut. For our sandwich, we don't need the whole log. We only need its soul, its most beautiful part, the thin top layer that everyone will see. Therefore, the best, straightest logs are brought to the factory. First, a real spa day awaits them. They are immersed in huge pools of hot water, or placed in chambers where they are treated with steam at a temperature of 200 degrees Fahrenheit. This is done to soften the wood and make it ready for the thinnest slicing in the world. After this, the log goes to a machine that is something between a giant pencil sharpener and an industrial slicer for delicacies. This is a peeling or slicing machine. Imagine a sharp, scalpel-like knife 10 feet long. It is slowly brought to the rotating log and begins to shave off a continuous wide ribbon of wood, just 1/8 or even 1/16 of an inch thick. This is our veneer, our precious ham for the sandwich. This wet, flexible sheet is then carefully dried in special chambers to make it stable, but to preserve its natural beauty. But what will be the bread in our sandwich? For this, we don't need supermodels. We go to another forest, where simple workhorses grow. Fast-growing and inexpensive species like poplar, birch, or eucalyptus. These logs go through a similar peeling procedure, but the ribbons are cut a little thicker. And this is where the main secret of the stability of engineered hardwood begins. Imagine that you took several of these thin wooden sheets. You lay the first one so that the fibers run lengthwise. You lay the second layer on top, but you turn it 90 degrees so that the fibers run crosswise. The third, again lengthwise. The fourth, again crosswise. And so on, creating a multi-layered pie where each layer is perpendicular to the previous one. Why is this so important? Because wood is alive. It always tries to expand and contract across the grain, reacting to humidity. But when you glue these layers perpendicularly, they seem to hold each other in a steel embrace. One layer wants to expand, but the other, lying perpendicularly, does not allow it to do so. This is a brilliant solution that makes the base of engineered hardwood incredibly stable and resistant to deformation. This multi-layered pie of cheap wood is sent under a hot press, where under huge pressure and temperature, it is glued into a single, strong block, like plywood. These are the muscles of our floor. Now it's time to assemble our club sandwich. We have the sole, a thin, beautiful veneer of expensive wood. And we have the muscles, a thick, stable base of cheap wood. They need to be connected. The base moves along a conveyor and passes under rollers that resemble giant paint rollers. These rollers generously pour a special, incredibly strong glue onto it. Our precious veneer is carefully laid on top of this sticky surface, and this whole structure is sent to the final hot press. With a force of hundreds of pounds per square inch, the press connects beauty and strength into a single hole. At the exit, we get a huge master sheet, from which individual boards will then be cut. But this is not a floor yet, it's just a blank. It's time for makeup and a manicure. Giant saws cut the large sheet into individual boards of standard width, for example, 5 or 7 inches. And here, each board goes to one of the most important machines, the milling machine. An incredibly complex system of mills and knives, rotating at a frantic speed. On one side of the board, they cut a long protrusion called a tongue, and on the other, an equally long groove called a groove. It is this system that will allow the boards to fit together perfectly during installation, forming a continuous, smooth surface without gaps. Now our board has the correct shape, but its surface is still a bit rough. It is sent for sanding. This is a whole line of several sanding machines, each of which uses finer and finer sandpaper. After this process, the surface of the board becomes as smooth as silk, ready for the final coating. And here, the real high-tech begins. The board enters a finishing line that looks like a car wash, only instead of water and soap, there is varnish and ultraviolet light. First, rollers apply the first layer of a special, incredibly durable varnish based on aluminum oxide. This is one of the hardest substances in the world, which makes the floor resistant to scratches. Immediately after application, the board passes under powerful ultraviolet lamps, and the varnish, which in normal conditions would dry for hours, hardens in a fraction of a second under the influence of ultraviolet light. Then a second layer is applied, and again a tan under ultraviolet light. The third, fourth, fifth. Sometimes it goes up to 7 to 9 such layers. As a result, we get a perfectly smooth, incredibly strong, and durable coating. That ultraviolet coating is not just a varnish. Aluminum oxide is added to its composition, one of the hardest minerals in the world, second only to diamond. From 7 to 9 layers of this coating are applied to the board, and each layer is instantly baked by ultraviolet light. As a result, we get a surface that is many times more resistant to scratches and wear than a traditional varnish applied to a solid board after installation. At the final stage, each board undergoes strict quality control. Inspectors with an eagle's eye look for any defects, scratches, uneven color, problems with geometry. Only perfect boards get a ticket to life. Robotic manipulators carefully stack them in boxes, indicating the type of wood, color, and dimensions. And so, having passed the path from 2 different forests, through hot baths, sharp knives, sticky waterfalls of glue, and an infernal ultraviolet tan, this brilliant creation is born, engineered hardwood. It took the best from nature, its beauty, and the best from engineering, its stability, to become the perfect floor for our homes, which is not afraid of either winter dryness or summer humidity. The engineered hardwood market in the USA is a giant that turns over more than $10 billion a year. And this is not just a stable market, it is growing rapidly, winning an increasing share from its older, solid brother, solid wood. Why? Because it's smarter, and the numbers prove it. The main superpower is stability. Thanks to its cross-layered, multi-layered structure, engineered hardwood is 50 and even 60% more stable than a solid board of the same species and thickness. What does this mean in real life? It means that it can be installed where ordinary wood would go crazy from humidity fluctuations, in basements, kitchens, bathrooms, and on a concrete slab. It is not afraid of underfloor heating. If one perfect log of precious white oak was sawn into a 3/4 inch thick solid board, a certain number of square feet of flooring would be obtained. And now, attention! If this same log were used to produce thin veneer for engineered hardwood, 3 or 5 times more finished flooring could be obtained from it. This means that to cover the same area, 3 or 5 times fewer valuable trees need to be cut down. This makes engineered hardwood a much more environmentally responsible choice. Every year, over 25 billion square feet of oriented strand board are produced worldwide. Imagine, this amount would be enough to cover the entire state of Delaware. Twice. Or to build a path around the Earth over 190 times. Plywood was once the king of the market, but the 80s changed everything. And today, OSB controls over 75% of American construction. But how is a material that changed the industry forever, born from young trees, through hot baths, giant graters, and infernal presses? Watch closely. At the end, you'll learn a secret that even builders keep quiet about. It all begins not in a waste warehouse, but in the forest. For the production of high-quality oriented strand board, preference is given not to random offcuts, but to whole logs, usually from relatively young, fast-growing trees like aspen or southern yellow pine. These forests are often managed and self-sustaining, which makes the process more environmentally friendly. When the logs, tens of feet long, arrive at the factory, they are not immediately sent to the workshop. First, a hot bath awaits them. They are immersed in long pools of hot water, or placed in chambers where they are treated with steam. This isn't just washing. This process, which lasts several hours, softens the wood and, most importantly, weakens the bond between the wood and the bark. After this sauna, the logs go to a debarking machine. Imagine a huge rotating drum with protrusions inside. The logs rubbing against each other and against the walls of the drum, and the bark flies off them like a husk. Bark removal is a critically important step, as bark lacks strength and does not glue well, so it is an undesirable impurity in the final product. Annually, factories in North America produce over 25 billion square feet of oriented strand board. This number is so absurd that it's hard to comprehend. Let's try. If you took all this quantity of panels and laid them out, you could completely cover the entire territory of the state of Delaware. Twice. Or build a continuous 1 foot wide path that would wrap around the Earth at the equator over 190 times. This is not just a lot, it's total domination. For decades, plywood was the king of the market. But in the 80s and 90s, this daring newcomer came onto the scene, and today oriented strand board controls over 75% of the sheathing market for walls and roofs in residential construction in the United States. This was a real quiet revolution. The cleaned, light, and still damp trunks are ready for the main event, transformation into thousands of thin ribbons. They go to a machine called a strander, or a flaker. This is the heart of the whole process. Imagine a giant metal disc rotating at a frantic speed, equipped with dozens of sharp, scalpel-like knives. The log is slowly fed to this disc, and it shaves off long, flat, chip-like ribbons, strands. This is not chaotic shavings. Each strand has parameters precisely set by engineers. The length can reach 6 inches, the width, about an inch, and the thickness, only a few hundredths of an inch. It is this geometry, this noodle shape, that is the key to the future strength of the oriented strand board panel. When ordinary boards are made from a log, a significant part of it, up to 50%, turns into sawdust, offcuts, and shavings. And in the production of oriented strand board, from 85 to 95% of the entire wood of the log is used. We will talk about this later, but practically nothing goes to waste. The strands are cut from the entire length, and the bark, sawdust, and the smallest particles are burned in furnaces to provide energy for the factory itself. This makes this material not only cheaper, but also much more environmentally responsible. The resulting mass of wet, fresh chips, resembling a huge pile of light noodles, is stored in special bunkers, and from there, it is sent for drying. This is a huge, multi-story drum, slowly rotating, half a football field long. Inside it, a high temperature is maintained, and while the strands are slowly tumbling, moving from one end to the other, a stream of hot air evaporates the excess moisture from them. The moisture needs to be reduced from 50 or 70% to only 2 or 3%. This is absolutely necessary so that the resin can properly soak the wood and glue it firmly. After drying, the strands pass through a system of huge vibrating screens, which sift out particles that are too small, for example dust, which will go to fuel for the same dryer, and pieces that are too large, which will be sent for regrinding. Now the perfectly dry and sorted strands are ready for impregnation. They enter a huge, slowly rotating drum mixer. While they are being mixed, a sticky chemical cocktail is sprayed onto them through special nozzles. The main ingredient is a waterproof resin, which will be our glue. The second important component is paraffin wax. It envelops each chip like an invisible raincoat, and it is this that will give the future-oriented strand board panel its famous moisture resistance. And now, the smartest and most important part of the process begins, which gave the material its name: orientation. The strands, impregnated with glue and wax, go to a long, wide-forming conveyor. Here, a whole system of mechanical choreographers works. Special discs, rollers, and combs that lay out the chips in a precisely defined order. First, the bottom layer is formed. The choreographers lay out the strands so that they all lie parallel to the long edge of the future panel, that is, lengthwise. Then comes the turn of the middle layer. Here the strands are laid out perpendicularly, that is, crosswise. And finally, the top layer is again laid out lengthwise. As a result, we get a thick, fluffy, 3-layer pie, where the fibers in each layer are perpendicular to the fibers in the adjacent one. It is this cross structure, which imitates the strength of plywood, that is the secret that makes oriented strand board incredibly strong in bending and resistant to deformation. This fluffy mat, which can be several feet thick, slowly moves to the final test, the hot press. This is a real industrial leviathan, a multi-story structure that creates colossal pressure and heat. The mat enters inside, and massive steel plates begin to compress it with a force of hundreds of pounds per square inch. At the same time, the press is heated to a temperature of 400 degrees Fahrenheit. This heat activates the resin, causing it to polymerize and permanently glue all the chips into a single monolithic shield. The wax also melts, even better impregnating the wood and filling microscopic voids. In a few minutes, the loose mass turns into a hard, incredibly dense, and hot panel. A huge master sheet comes out of the press, which can be 50 feet long and 12 feet wide. While it is still warm, its edges are trimmed with diamond saws, and then giant saws cut it into standard building formats, most often 4 by 8 feet. Markings with information about its thickness, class, and compliance with building codes are applied to the surface of the panel. Sometimes special tongues and grooves are cut into the edges so that the sheets fit together perfectly when installing a floor or roof. The finished, perfectly rectangular sheets are stacked in high piles by robotic manipulators, wrapped in protective film, and sent to the warehouse. And so, having passed the path from a whole log through a giant grater, a sticky shower, and the fiery embrace of a press, this honest, unpretentious, and insanely strong material is born, ready to become the silent but reliable foundation for thousands of homes across the country. For the construction of an average single-family home with an area of 2,400 square feet, approximately 8,000 square feet of oriented strand board panels are needed. This material goes into everything. They sheathe the exterior walls, creating a strong and rigid frame. They make a solid sheathing on the roof, on which shingles are then laid. And of course, they make the subfloor, which is the foundation for all rooms. In essence, the entire modern American house is a wooden frame wrapped in a strong cocoon of oriented strand board. Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground. That's so much steel that it would be enough to build several aircraft carriers. Imagine, these metal giants don't rise up into the sea but disappear underground, holding our cities, dams, and ports from destruction. But how is a perfect steel profile, with a tolerance smaller than the thickness of a fingernail, born from a pile of old scrap? What happens in the furnaces with 3,000 degrees and on the rolling mills where metal is formed at the speed of a car? Watch until the end, and you will discover the secrets of production that are usually hidden from prying eyes. Annually in the United States, hundreds of thousands of tons of these profiles are produced and driven into the ground. To imagine this weight, Think of an aircraft carrier. One such ship weighs about 100,000 tons. This means that in a year, the country creates enough sheet piles to build several such steel floating cities. This is an endless stream of metal that goes underground to hold what is on the surface. It all begins, as in many stories about steel, at a huge scrap metal yard. This is a place where old ships, building structures, and industrial junk get a chance for a new, noble life. A giant crane with an electromagnet gathers tons of this metal and loads it into a huge ladle, which is sent to the melting shop. There, in the roaring hell of an electric arc furnace, where the temperature reaches 3,000 degrees Fahrenheit, this scrap is transformed into a boiling lake of liquid steel. Special alloying elements are added to this melt so that the future pile is not only strong, but also resistant to corrosion, as it will have to work for decades in moist soil. Next, this fiery river passes through a continuous casting machine, where it cools and solidifies, turning into a long, red-hot steel billet called a slab. This is our blank, our formless piece of dough, in which all future strength is already embedded. These hot slabs, cut into pieces of the required length, are sent to a reheating furnace. There, in a controlled heat, their temperature is again brought to the ideal plastic state, about 2,200 degrees Fahrenheit. They become soft and pliable, ready for the main transformation. And now the most interesting part begins: rolling. The red-hot slab comes out of the furnace and enters the rolling mill. It's necessary to form not just a symmetrical profile, but a complex shape with bends and, most importantly, with a perfect lock on the edges. The rolls of the rolling mill for sheet piles are not just cylinders. They are real sculptors of steel, having complex shaped grooves. The slab flies into the first pair of rolls with a roar, which squeezes it and begins to form the main profile, usually Z-shaped or U-shaped. Then it passes through the next pair, which further refines the shape. And so, step by step, passing through dozens of such rolls, our flat bar is transformed into a long, ribbed ribbon before our eyes. We talked about locks or interlocks. Well, the tolerance in their manufacture is only a few hundredths of an inch. That's less than the thickness of a fingernail. The red-hot steel ribbon flies along the rolling mill at the speed of a car, and at this moment, the rolls form a lock on it with such incredible precision. This is necessary because at the construction site, workers will have to connect hundreds of such piles. If the tolerance is even slightly larger, this giant industrial zipper simply won't close. On average, 1 square foot of a sheet pile wall weighs from 20 to 40 pounds. And now imagine one pile 60 feet long. Its weight can easily exceed 3,000 pounds. This is like the weight of a small sedan, concentrated in one long, thin piece of steel. And these piles, interlocked together, form a wall capable of withstanding the pressure of earth and water, equivalent to the weight of dozens of trucks pressing on it simultaneously. But the most important thing happens at the edges. The last sets of rolls, finishing rolls, form the most complex element of the pile, the lock or interlock. On one edge of the pile, a groove is formed, similar to clasped fingers, and on the other, a protrusion, similar to a thumb. These elements must be formed with an accuracy of a fraction of an inch. If the lock is too tight, it will be impossible to connect the piles at the construction site. If it is too loose, the wall will not be sealed and will leak water. Therefore, the rolls with incredible force, but at the same time with precision, press out this complex profile along the entire length of the red-hot steel ribbon, which can reach several hundred feet. The hot, perfectly formed pile crawls out of the last roll and along a roller conveyor goes to a cooling table. There, slowly cooling, it acquires its final strength. After cooling, it is checked for straightness and, if necessary, straightened on a special straightening machine. Then it's time for the final operations. A huge cold saw, with a deafening roar, cuts off piles of standard length from the long ribbon. Inspectors take special templates, or gauges, and carefully check the geometry of the locks. They check whether the fingers and groove fit perfectly, whether there are any defects that could prevent connection. This is a guarantee that at the construction site, somewhere in a deep pit, these steel sheets will connect into a single, strong, and waterproof wall. Some piles may undergo additional processing. A special sealant is applied to their locks, which, when connected, fills microscopic gaps, making the wall completely sealed. The finished checked piles are collected into bundles, marked, and loaded onto railway platforms or barges by giant cranes. And so, these steel soldiers, born in fire and pressure, are ready to set off for their service, to go underground and silently, invisibly to all, bear the weight of the earth and the pressure of water, making the construction of the most daring modern projects possible. The lion's share of sheet piles is used in marine infrastructure, the construction of ports, piers, docks, and breakwaters. They are the silent guards of our coastlines. A huge number go to flood protection, forming the core of dams and levees along rivers, especially in places like New Orleans. And of course, they are indispensable in large cities, where a deep pit needs to be dug for the foundation of a skyscraper, right in the middle of dense development. This steel wall, driven into the ground, prevents neighboring buildings from sliding into the pit. So these hundreds of thousands of tons of steel are not just production statistics. They are a measure of our ability to tame the land and water, to build where it was previously impossible, and to protect our cities from the elements, one precise lock at a time. The finished piles lie in neat bundles, resembling giant packs of pencils. The first move is made by overhead cranes. A huge beam moves under the ceiling of the workshop. Powerful electromagnets or special traverses with several hooks hang from it. With a hum, the crane descends, and with a metallic clang, it picks up a whole bundle of piles, which can weigh 30 tons. The crane operator transports this cargo and carefully places it on a transport vehicle. And here we have two main paths, by land or by rail. If the construction site is relatively close, the piles will go by truck, but these are not ordinary semi-trucks. To transport 60-foot piles, special extendable platforms are needed. This is a very long trailer that can extend like a telescope, reaching an incredible length. Due to the length of the cargo, the driver needs incredible skill to navigate turns. Often, such cargoes are accompanied by special vehicles with flashing lights, which warn other drivers and help in difficult sections. Every turn at an intersection is a slow, calculated maneuver that requires all the available space. If the distance is long and the order volume is huge, the railway comes to the rescue. Bundles of piles are loaded onto long, flat car wagons. This is much more efficient for large batches. An entire freight train, loaded with hundreds of tons of steel piles, looks like the spine of some prehistoric beast. With a rhythmic clatter of wheels, it travels hundreds of miles, crossing states, to deliver its cargo to the station nearest the construction site. There, the piles are reloaded onto trucks for the final throw of a few miles. Every year, new icebreakers are launched around the world, giants capable of cutting through ice several meters thick. These are ships whose mass can exceed 20,000 tons, more than the weight of an entire stadium filled with people. But how is this steel beast born from 1,000 metal blocks? What does the moment look like when a multi-story crane, with millimeter precision, installs a piece of the hull weighing hundreds of tons? And what happens when the ship's bow first cuts into an ice field, and the hull shudders from an impact similar to an earthquake? In this video, you will learn what is not shown to the public, from digital ghosts in design bureaus to the moment of truth when an icebreaker meets its first ice. Watch until the end, because a secret that few know awaits you. It all begins not with the roar of hammers, but with the silence of a design bureau. Before a single piece of metal is cut, thousands of engineers spend years at computers. They create a detailed three-dimensional model of the future vessel. This is a digital twin, where every screw, every weld seam, every meter of pipe is calculated. Using powerful computers, they simulate the most extreme situations. How the hull will interact with ice of different thicknesses. How the ship will behave in a hurricane. How it will withstand a collision with a multi-ton hummock. These are virtual crash tests, where the cost of an error is only processor time, not human lives. Only when every aspect of this digital ghost is perfected are the drawings sent to the workshop. Icebreakers are not built whole, like a model ship in a bottle. They are assembled from giant blocks, like a colossal Lego set. In huge workshops, the size of several football fields, the cutting of steel begins. For icebreakers, special low-temperature, high-strength alloys are used. Ordinary steel in the Arctic cold becomes brittle as glass and can crack from a strong impact. But this one retains its ductility and strength even at a temperature of -60 degrees Fahrenheit. The sheets of this steel can be incredibly thick. If a regular ship has a hull thickness of less than an inch, then an icebreaker in the so-called ice belt, the area that contacts the ice, can have a thickness of 2 inches or more. This is thicker than a bank vault door. Plasma cutters, controlled by a computer, with a hiss and showers of sparks, cut thousands of parts of the future hull from these sheets. Then these parts are welded into sections, and the sections into huge multi-story blocks. Each such block is already a finished part of the ship, for example, a piece of the engine room, or several cabins, already with part of the pipes and fasteners. Every weld seam here is a matter of life and death, so it is checked with X-rays and ultrasound to ensure the absence of the slightest defects. A symbolic moment arrives, the laying of the keel. On a huge construction site called a slipway or a dry dock, the first central block is installed. This is the spine of the future giant. And to this spine, like ribs to a spine, other blocks begin to be attached. Giant gantry cranes, looming over the entire dock, come into play. With incredible precision, they lift these multi-ton pieces, weighing hundreds of tons each, carry them through the air, and with millimeter precision, set them in place. Welders, resembling astronauts in their protective suits, connect these blocks into a single, monolithic hull. Gradually, day by day, a giant steel beast grows from these separate pieces, and its shape is its main weapon. The bow of an icebreaker is not sharp, like a regular ship's. It has a special, spoon-like shape. It doesn't cut the ice. It crawls onto it, and then, under the action of the colossal weight of the entire vessel, and this can be from 15 to 20,000 tons, it simply breaks the ice, like a person stepping on thin ice on a puddle. Its bottom is rounded, without a protruding keel, so that after breaking the ice, it can easily push the fragments aside and not get stuck. While the hull is growing, the heart is installed inside, the power plant. An icebreaker needs not so much speed as colossal, unstoppable power and torque. Therefore, most modern icebreakers are diesel-electric. Imagine that a whole power station is inside it. Several giant diesel engines, each the size of a bus, turn generators, producing megawatts of electricity. This energy is then supplied to huge electric motors, located in the aft part of the vessel, which directly turn the propellers. This scheme allows for maximum power on the propellers instantly and very precise regulation. The total power of the power plant can reach 50,000 horsepower, enough to power a small city. The propellers of an icebreaker are also a work of art. They are made of super strong stainless steel, have a huge diameter, and thick blades like the wings of an airplane, capable of withstanding impacts from ice flows weighing tons. When the hull is assembled and the main equipment is installed, the moment of birth arrives, the launch. If the ship was built in a dry dock, the dock is simply slowly filled with water, and the giant ship smoothly floats off its supports. If it was built on an inclined slipway, it is much more dramatic. The supports are cut, and the multi-thousand-ton machine, gaining speed, slides into the water with a creak and a roar, raising a huge wave. And so, this giant for the first time sways on the waves. But it is still far from ready. It is just an empty steel box with engines. It is towed to a fitting-out quay, and here the most complex part begins: the outfitting. Hundreds of miles of electrical cables, thousands of meters of pipes for water, fuel, sewage, ventilation are laid throughout the ship, forming its circulatory and nervous systems. Living modules, wardrooms, a galley, a medical unit are installed. Navigational equipment is mounted on the captain's bridge. Radars, sonars, satellite systems, powerful deck cranes, scientific equipment, a helicopter pad are installed. The entire ship is covered with a thick layer of thermal insulation. And then the time for the final exam comes. The Icebreaker goes out into the open sea, away from the shore. On board, not only the crew, but a whole army of engineers, representatives of the shipyard, classification societies, and the customer. Each of them with their own notebook and a list of hundreds of items that need to be checked. It all starts with the basics. Full ahead. The command sounds from the bridge. The engine room comes to life, the diesel generators go to full power, and the giant propellers begin to accelerate the multi-thousand-ton machine. Engineers with sensors check everything: hull vibration, engine temperature, pressure in the fuel systems. The vessel accelerates to its maximum speed on clear water, which is usually not very impressive, about 17 knots. Then the command, "Stop engine." And everyone watches how many miles this giant will need to come to a complete stop. This is called the inertial coasting. Next, maneuverability. Hard to port. And the rudder is turned to the maximum angle. Everyone watches how large the turning circle will be. That is, how wide a circle the Icebreaker will describe at a full turn. They test reverse, reaction speed to commands, the work of the autopilot. Every system, from the large engines to the small pump in the toilet, is turned on and off, checked under maximum load. They even conduct a so-called blackout test. They deliberately turn off the main power to check how quickly the emergency diesel generators will start and restore the operation of vital systems. Only when every item on the long list is checked off. But all this was just a warm-up. The real exam is ahead. Winter comes, and our Icebreaker, fueled to the brim, heads north, towards its true calling: the first encounter with the ice. This is the moment of truth. The captain directs the vessel straight into an ice field. From the bridge, you can see the horizon turning into an endless white desert. First comes young, thin ice. The Icebreaker passes through it like a knife through butter, with a light rustle and crackle. But then the ice gets thicker. And so, the vessel at full speed crashes into real, multi-year ice several feet thick. A deafening blow sounds, shaking the entire hull. This is not like a collision. It's like the sound of an earthquake. The whole ship vibrates, dishes in the cupboards rattle. The specially designed bow crawls onto the ice, and under the weight of thousands of tons of steel, it breaks with a loud crack, spreading giant cracks. The fragments, the size of cars, scrape against the sides with a grinding sound. And so, meter by meter, the Icebreaker makes its way. Special sensors, installed throughout the hull, record the pressure that the ice exerts on the hull and transmit the data to the engineers. They check whether the real loads correspond to those calculated in the computer models. It returns to port for final adjustments. Imagine thousands of glass threads, thin as a hair, combined into a single river, are transformed into a material that is already challenging steel. This isn't science fiction, but modern production of fiberglass rebar. Every year, the world spends billions fighting rust, repairing bridges and parking garages destroyed by corrosion. But there is a solution, a composite that is twice as strong as steel, 4 times lighter, and doesn't even know what rust is. The market for this material is growing by 12% annually, and today you will see how a building material of the future is born from hundreds of bobbins and a barrel of resin. It all begins at one end of a huge workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall, several yards high, hundreds, and sometimes thousands, of huge bobbins are installed in neat rows. On each of them is wound the thinnest glass thread, or roving. This isn't the glass that windows are made of. This is a special fiberglass, which is produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. They will be our skeleton, our internal army, which will give the rod its insane strength. From each of these hundreds of bobbins stretches its own separate thread, and they all gather into one thick, fluffy bundle. It's like thousands of streams merging into one large river. This dry white bundle is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Each of the thousands of threads must be tensioned with the same force. If one thread sags and another is over-tensioned, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment baptism in resin. The dry glass bundle is slowly immersed in a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat, that will grow on the glass skeleton. This is a complex chemical cocktail. The base is usually polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will start a chemical reaction and force the liquid to turn into a solid plastic. Also, various additives can be added here. Pigments to give color, ultraviolet inhibitors so that the rebar is not afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to soak every, even the tiniest fiber. The bundle must be completely submerged in this resin so that not a single dry spot remains. The soaked, heavy from sticky resin bundle comes out of the bath and heads to the point of its birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round, polished hole, the diameter of which exactly corresponds to the diameter of the future rod. The die is heated to a certain temperature. When the wet bundle is drawn into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass together, forming a perfectly round rod. Third, the heat from the die starts the initial stage of the chemical reaction of hardening, or polymerization. The resin begins to turn from a liquid into a gel. At the exit of the die, we already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special bundle of the same fiberglass is wound onto it. A thin, resin-soaked thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled on the sticky surface, which sticks firmly to the resin. Now our rebar has not only strength, but also teeth with which it will hold onto concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization furnace. This is a long chamber that can stretch for tens of feet, inside which a high temperature is maintained, usually 400 Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively connect with each other, forming a strong, rigid, three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material, which firmly binds millions of glass fibers into a single monolith. It's like baking a pie. While the rod slowly moves through this hot tunnel, it acquires its final, stone-like hardness. But what pulls it through this whole long path, from the bobbins to the furnace? At the end of the line stands a special pulling device, which gave the whole process its name. Usually, these are two caterpillar mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads, and at a constant, precisely calibrated speed, pull it towards themselves. It is they who create the force that pulls the fiberglass through the resin bath, through the forming die, and through the furnace. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor appears an endless, perfectly even, hard and hot fiberglass rod. The final chord is cutting. Across the line is an automatic saw. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward movement, and with a sharp whiz, cuts off a piece of standard length from the endless ribbon, for example, 20 or 40 feet. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And so, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and furnaces, have turned into a light but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungles. The fiberglass rebar market is not yet a giant like the steel market, but it is the coolest and most daring newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are simply insane. It is expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now about the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sounds boring? Now imagine it in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it is limited by weight. Or, for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can calmly carry whole coils or bundles of fiberglass rods, whereas a crane is needed to move steel. This is a colossal saving on logistics and labor. Second is strength, and here fiberglass simply enters the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing an ordinary rope with a climbing rope. At a smaller thickness, it withstands much greater loads. But the main trump card, the real superpower of fiberglass, is its war with rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load, it's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. Rust increases in volume and literally tears the concrete from the inside. Annually, the United States spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years, and a structure with fiberglass rebar is calmly designed for more than 100 years.